question now. This is show a live demo. And this is the guest running the 3D workload at Unity Heaven. And you will see during the live migrations, the bus ID will be changed. And there is a small pause. And this is the live machine, how it works. And OK, yeah, I will show my slides now. OK, so my section is the live migration support for GPU with SR-IOV. And this is basically a project collaboration from the Alibaba and the AMD together. And we will have talking about two parts. And my part will mainly focus on the hypervisor and the QEMU part. And the jury from AMD, the architecture from AMD will introduction more specific to the GPU specificities in the second part. When we're talking about the GPU virtualization, basically there are several solutions. The first one we all know it is like the pass-through solutions. And then it is the SR-IOV solutions, which is we are working on now with the AMD. And the third solution is called the mediated pass-through. And we know Intel GPU and NVIDIA GPU actually is using this solution. And there is also other solutions like Virtual GPU, Acoda, and also others. But as of now, these other solutions is not production level or it's not commercialized in the data centers. So the left three solutions, pass-through solution, SR-IOV solution, and the mediated pass-through solution. These are production level and commercialized. And they actually are full GPU capabilities. That means whenever the workload running in the native site, you're able to run it in the guest. So this is the full GPU capability and full features. They also, for the SR-IOV solution and the mediated pass-through solutions, they actually have advanced features. For example, you can support the live migrations. So we are talking about the SR-IOV live migration today with the second solution. So I will put more time on this slide. So when we see the difference with the pass-through and SR-IOV, so you will see there is very similar on the QEMU point of view. They both have BDF, a PCI device assigned to the guest. The QEMU actually did not know whether it is a pass-through or it is SR-IOV. Simply, it is treated as the PCI device assignment. But the difference is, with the pass-through solutions, there is no host driver in the host site. So basically, you don't know, the host actually did not know when the GPU actually was doing. You are not even to know what's the temperature, what's the frame buffer usage, the whole guest was used. So here is the problem is the pass-through solutions, because he lack of the information. So it is difficult to support live migration. But the things difference changed in the SR-IOV solutions. So the SR-IOV, there is a PF driver, there is a VF model. So the PF driver actually knows everything in the guest side. So he is able to collect the information. So what he's doing in the GPU side. So this is possible to do the live migrations. And we are talking about now and see how we will support these features. Of course, mediated pass-through, this is a framework like about 2 years or maybe 3 years ago. This is a new framework. And we know Intel actually already supports the GPU live migrations with the mediated pass-through 2 years ago. And NVIDIA, I know there is a few days ago, also sent out the patch to support the GPU live migrations. So yeah, it's good things. There is both the AMD, Intel, and NVIDIA will going to support live migration. Yeah, this is good things. Okay, let's see the close look at the SR-IOV GPU live migrations. So there is no fancy things here from the QEMU point of view. And also from the host side, there is a VFIO PCI model. There is a VFIO base driver and a VFIO type 1 MMU driver, also with the K-mean driver. And this is the very similar thing how pass-through works. But the difference is there is an additional model. We call it GIM, GIM.ko. So this is the SR-IOV GPU host driver. So what's inside this driver? This driver actually controlling how GPU resource was partitioned, how GPU was time sliced to the different VFs. So you will see SR-IOV GPUs, yeah, it's same thing like the MDV frameworks. It is also have the partitioned resource. It also have the time slice scheduling between each VFs. So we will see from the guest point of view, he will assign one of the VF. And then the guest driver access the MMO, access the doorbells, access the frame buffers. So all of this resource was exposed from the VF interface. So the VF and the PF actually is the PCIe SR-IOV interface. But it did not define how the GPU was visualized. So this is how Zheng Java did. So the Zheng Java, just the introduction, he controlled the internal GPU resource. He controlled how GPU was visualized for each VFs. So right now, for the SR-IOV GPUs, there is a graphic engine support. It was partitioned by each VFs. And also, there is a video encoder engines, which is also partitioned into the multiple VFs. And the Zheng Java controlling all of these things. The current status of our project. First of all, this is the collaboration between Alibaba Cloud Virtualization team and the AMD Virtualization teams. And actually, this is still a product solution. It is based on the MI25 AMD GPU. Right now, we already support rendering 3D rendering migrations. And it is under developing to support the medium workload migrations in the near future. We also support the VF with checkpoint support, save to disk, and restores. So regarding to the service downtime, currently it's about 500 milliseconds with 1 gig graphic memory. Yeah, it's 500 milliseconds downtime is a little large, but it is still put up codes, and we believe there is still a lot of room to improve in the future. I show some evaluation results. The first thing is we have compared with the idle workload and also with the Unity Heaven, which is keep the direct GPU rendering engine and busy. So we also compare with the smaller frame buffer size with the 512 meg, and also with the larger frame buffer size. It's around 1 gig memory. So we will say with the bigger frame buffer size, with the busy of the GPU, so you have the larger service downtime. And with the idle case, if it is smaller buffer size, it's about 350 milliseconds service downtime. Here is the cumulative level, so how we implement to support the GPU line migrations with SR-IOV support. Basically, cumulative have several stages to support the line migration. First thing is the migration start. When the migration starts, it will send a global notifications. So we get this notification and we tell the Zheng Java, Zheng is the host Java, to tell them now prepare the migrations we are going to do the migration in following. And then we'll go into the next stage is the log sync stage. So in this stage, there is a literally round copy, and we collect the dirty pages. And in this stage, actually, we do the entire FV frame buffer memory copied to the target site. Of course, at this stage, the CPU and the GPU are still running. So it is possible that once we copy the entire frame buffer size, there is still a frame buffer was dirtied. But this is OK. When we go into the next stage, the CPU was paused. And then we remove the GPU scheduler. At this time, GPU was stopped. Of course, you need to wait the GPU to jam his current workload. And then we will collecting the information which is dirty in both the frame buffer size and also because the GPU will access the system memory and also the frame buffers. So we will collecting these dirty pages and copy to the target site. So after that, everything is ready. So we'll get the notification to the target site. So you get everything ready. So you are ready to reschedule the GPU and put the VMs restart. OK, so what's the challenges we have? The first thing is when we do the live migrations, there is two processes. One is the CPU, another is GPU. So the first question is, shall we stop the CPU first, or shall we stop the GPU first? The problem here is, the answer is you can do either way. So if you stop the GPU first, the GPU hardware remove the scheduling from the scheduling. The problem here is the CPU was still running, and he was still pushing the context of the DMA request to the device driver. So the DMA request will accumulate. But if this time, accumulate more and more, and if it exceeds a value, for example, 2 seconds, so it is possible when we migrate this VM to the target site, the target will be a TDR. TDR means the timeout detection recovery. So under the Windows, it's possible that it will crash the VM. So our solution is we will stop the GPU first. We will stop the CPU first and then the GPU. But in this case, if you stop the CPU first, then the GPU will still run in the DMA, and sometimes you need to wait the DMA to complete, and it's like sometimes it's like the 100 milliseconds. And once the CPU stopped, the server downtime is very critical. So at this time, we will actually preempting the workload. So this is how Jerry's team will working on this. It is working on this. And regarding the second challenge here is the memory tracking. So we know when we do the live migrations, the first thing is how to track the dirty memories. So here the dirty memory is from the GPU side. So GPU will access the frame buffer. GPU will also access the system memory. So here is the problem is how GPU to tracking these memories. Fortunately, we already resolved this. And then the workload preemption I just already talked about. So when we stop the CPU and the GPU is still running and you can't wait, you need to preemption the workload. And another thing is the GPU internal status save and restore. GPU is very complex. There is page tables, there is internal MMU interrupt status, and also the register information, and so all things need to save and restore. And Jerry from the AMD will talking more about this. And yeah, this is the pretty much from my point. Let's welcome Jerry from AMD.
Seems that we are short of time. So I'm from AMD, Jiang, working on the GPU virtualization for a few years. So today I'm going to introduce a little of the live migration that we did on the SR-IOV. I think here is some backgrounds. I will start with some background introductions before I jump into the live migration. So you might or may not know that about the SR-IOV. So this is the hierarchy of the SR-IOV defined by the PCI SIP. Since I'm running out of time, so I will just skip this. So the end point is that we have devices that connect to the root port or connect to the root port through the bridges. So each one of the function, you are going to enable the SR-IOV with a PF function with multiple VF functions on bus. So with the SR-IOV, we have some advantage over the solutions that we use the PCI 6 standard. And the lightweight vendor-specific drivers that Xiao just mentioned is the Zheng driver that we're running in the host. And the VM, of course, they use and modify the OS and applications. And it can also use our standard GPU drivers in the guest VM. The support of the host VM will be a privileged version that manages the partitioning. And the guest, right, even though from the total generation, we are saying that we support up to 16 virtual functions with one physical function on a single GPU. And if we have multiple, so on one GPU, you can support, of course, 16 guest VM, and more GPU will support more guests. And in the guest, you have a whole set of a GPU that the feature set of a computer, of the GPU like DirectX, OpenGL, OpenCL, Welcome, and Welcome. And you also support the H.264 and HEVC encoding. The performance-wise, the guest driver actually interact with the GPU directly without any software layer interactions. So it eliminates all of those software data copy overhead that we encounter in the traditional virtualization solutions. So here's a diagram about a high view on the KVM, the SR-IOV solutions with the KMD, with the AMD that on the host, we have the GPU drivers also. It talks with the PF, the PCI config spaces and the resources. On each VF, it shows up as individual VF and GPU buses, GPU devices, and the guest. And underneath, we have multiple of the engines that with the SR-IOV scheduler, as Xiao mentioned, that we have the time slides that partitioned for each engine. They can switch individually by themselves. So in the driver stack, the PF driver, they do the initializations, they do the error detections, and they also do the reset if there's error was found, and the light migration operations, of course. And on the guest driver, I think we already mentioned a lot of this, like it's independently. On the guest, we provide each guest, each GPU with independent RAM buffers, intra-vectors, dedicated frame buffers, the doorbell resources, and GPU state and GPU VMs. It interacts the GPU hardware through the VF GPU resources. The guest driver actually is aware of the wall switches that while you switch from one VF to another VF, or we call it context switches. All of those APIs that you saw or you encountered on the bare metal OS, you're going to see exactly the same on the guest. For the remote, we are going through the either Windows API, RDP, or Horizon View, TLTC, or HTX3. This is the background that we are going to need when we jump into the migration. So normally, when you have a pass-through devices, like we talk about a lot of lab migration solutions today and yesterday, right? So normally, when you have a normal pass-through devices, the hypervisor normally has some difficulties. Either you have to insert or implement something special in the get driver, like you have difficulties, say, stop the devices, or get the resources device, the device state. You copy the resources dedicated memory over, or you restore or initialize the target devices with the content after the migration. And also have some difficulties, say you have to restore the dedicated frame buffer, or the notify your guest driver saying you have to perform all of those operations to save, restore all your information over. But with SR-IOV, like on PF side, it's able to access to everything, actually. You can take the snapshot of the frame buffer, take the snapshot of GPU state for the VF. You can stop or start a VF running. I can also restore the snapshot of target frame buffer content, or restore the target VF GPU's contents. And the guest is simply migrate the 3D rendering. So all those preempted that at the migration time, if a command was not finished and it stopped in the middle, after the migration, I can resume from the point where it stopped it and going forward. And it can suspend the interrupt, and while coming back, we're going to resume it as well. So it's seamlessly like you just pause by a few 100 microseconds or maybe later, and then you will continue. So on a VF migration, right, on source, the GPU V driver, the GPU V driver, we can do a lot of stuff, like I just mentioned, like you schedule the time slides, you can stop it, or you copy the frame buffer, or system memories over, or the non-node code, and you also copy the VF GPU. So on the target, on the GIM driver, it will restore and restore all of those memories, non-local, local, and the GPU state. Just like I demoed that on the diagram, that the VF migration, you don't need necessarily to migrate to exactly the same VF numbers. You can migrate differently. And the GPU state, what a VF has is just part of the GPU state. So you migrate the partial of the state of your GPU, your VF only from source to the destination. So after migration, you don't need to do the reinitialization because the status was already migrated over. The preempt command is continuing to run. It's good that I don't need to show the demo now. We already showed the demo at the beginning. So at the beginning, when we showed the demo, right, you saw the device was, the screen was paused for a little while. This is the downtime, and we know that we have challenges over there. So a few challenges from GPU's point of view. We have three, right? So first one is the dirty page, frame buffer dirty page. At this time, I think just between those two screens you're curious, we should know that what page was dirty. And fortunately, our hardware actually have these solutions. But in the prototype, we haven't implemented this solution yet. And then there's a non-local memory dirty pages. I think we talked about a lot of this, right? Normally, we have IVMU trackings. I think this one, the current CPU doesn't support, and I'm not so sure that our next generation of CPU from AMD, like ROM, we are going to add on those dirty page trackings for IVMU. So later, you're going to see that we have a driver. We know that what's dirty from the GPU that we are running on. And we also know that there's some QEMU trackings. I think we talked about this. I don't want to repeat it. And then there's another solution that we can go through the GPU's GPU VM. We know the GPU VM has the information that which page we access in the system memory. We can go through that and take time, but it takes time. It would require some additional shadow pages, but this is also doable. The third one is the GPU compatibilities, like different generations. You might not be able to migrate from Vega 10 to Vega 20 or something new new GPUs later. Or if there's a firmware difference, you might not be able to do it. Some GPU graphic driver version, you might encounter that those handlings are different on the same GPU. So we provide certain APIs for QEMU or hypervisor applications to check whether the test and source are the same. If they come back as compatible, then you can go ahead with the migrations. So this is roughly what we have about blind migration. But it's a summary. I know we're running out of time, but with summaries that the SR-IOV virtualization has some benefits here. It's a PCI compliance. So it natively fits into the KVM architect. You don't need to do anything extra. It has enhanced security. So AMD's GPU has hardware protections for the GPU state and the frame buffer isolations. So none of those one VF cannot access to the other VF or either PFs. But PF is able to control all of the VF status. And it has a low of TOC. So the total cost of ownership is pretty low because the GPU hardware resources can be partitioned in any way you like to have. And it also is a live migration friendly. So we have APIs on host for QEMU to manage all of my migrations. On the guest side, you can see that there's a complete compute of graphic features all available on any guest of VMs. So this is, hopefully I didn't run over time. Okay, so this is what I have for the live migration on GPU VF. Any questions for us? Okay.
We have time for just one question.
Yeah. Sorry.
Since the VF GPU snapshot will copy to system memory, whether or not we should reserve the system memory in advance for this stuff?
Oh, I will let Xiao to answer these questions. It's about
actually, I think
memory
we
reservation.
don't need to reserve the memory advance. And actually, yeah, you can do this for performance regarding it. And you can also dynamically allocate, because we can transfer this buffer literally, and you don't need to allocate the whole of FB size copy in the system memory side.
Yeah, actually, we have an API for the QEMU to query that what memory is dirty. So in the period of time, I'm going to tell you that I need how many pages. You can dynamically allocate it. You don't need to pre-allocate it. As far as that, and you can go through a few cycles, right? Don't need to copy it in one chunk, really.
Okay, thank you. We are unfortunately out of time.
Oh, actually, you can approach me after this. Sorry.